Reflecting on the geopolitical landscape following the September 11th attacks on the World Trade Center and the Pentagon, Paul Virilio suggests that the landscape of contemporary war is indistinguishable from an industrial accident. Ruminating on the September 21, 2001 explosion at a fertilizer factory in Toulouse, which was initially reported as an extension of al-Qaeda's attacks on New York, he concludes that the confluence of accident and war into one risky geopolitical act, quote, promotes a fatal confusion between attack and accident, unquote. Virilio's always cheerful reading of this set of circumstances leads him to imagine a future, quote, great accident, of which industrial accidents and terrorist attacks are only ever prefigurations, unquote. In my talk today, I want to follow out this confluence of terror and accident in the context of digital infrastructure to think about how minimal computing is a security feature within the shadow of Virilio's great accident. Specifically, I want to think about accidents as a side effect of complexity and how this is entangled in the scales of big data. We have long known, even if only on an unconscious level, that software basically doesn't work. But now that the fragile tissue of the internet sustains our day-to-day lives, the growing specter of software accidents becomes a structuring feature of contemporary anxiety. Consider the recent Twitter meme in which network engineers offer various lists of what actually holds the internet together. Search on Twitter and you find a list of things dominated by baling wire, scotch tape, peanut butter, prayers, hopes, bubblegum, and band-aids. This morbidity is widespread in technical circles. Quinn Norton's aptly titled "Everything is Broken" references this meme by claiming that, quote, it's hard to explain to regular people how much technology barely works, unquote. She continues, quote, written by people with either no time or no money, most software gets shipped the moment it works well enough to let someone go home and see their family. What we get is mostly terrible, unquote. As an example, Norton traces Off the Record, or OTR, which is an encryption program that can be dropped into a variety of IM clients for truly secure conversations. OTR is great and thoroughly vetted for errors. However, it relies on a library called libpurple that leaks private and secure data like a sieve. The reliance on badly written libraries was also behind famous bugs such as Heartbleed, which is a serious vulnerability in the OpenSSL library that provides encryption to essentially everything. Errors like these result from project complexity, the reliance on other libraries, the need to get maximum features on a minimal budget, and the fundamental laziness of most programmers. Complexity is also one of the great features of programmable computers. It gets us the MapReduce architecture that powers Google search, Facebook's global public sphere, and the dubious ability to buy things using our faces as a feature of the new iPhone. However, as bugs like Heartbleed or the recent ransomware hijackings of NHS hospitals make clear, complexity, almost by its nature, introduces the inevitability of bugs, and by extension, accidents. In a blog post for the Minimal Computing Working Group, Gentry Sayers iterates possible definitions of minimal computing, offering 10 possible meanings, which you can see here. I want to add to this list minimal complexity, which might be another iteration to consider in the context of Virilio's great accident. Minimizing complexity cuts across a couple of Sayers' definitions, including minimal use, minimal consumption, and most importantly for me, minimal externals. Considering the last of these, Sayers uses externals to refer to issues of access and power in infrastructural systems, suggesting that, quote, attendant issues of power and self-organization shape an array of minimal computing practices, unquote. However, I want to differentiate complexity from Sayers' use of externals to remind us that complex entanglements are not always so obviously institutional. Many of the power relations that flow through our digital scholarly infrastructure are structured at the unseen and under-considered level of the software itself. As an example, consider a basic LAMP stack web application. LAMP is Linux, Apache, MySQL, and PHP, a collection of linked tools, a stack in web development terms, that stack on top of one another to describe a standard application environment of operating system, which is Linux, web server, Apache, data store, MySQL, and programming language, which is PHP. If you host your professional website on WordPress, you are using a LAMP application, possibly without realizing it. While your professional website may seem relatively simple, and it probably is in comparison to a website like Facebook, according to Rapid7, a database of published vulnerabilities in open source software, since 2004 there have been 413 vulnerabilities found in WordPress, which all things considered isn't terrible, 3,010 in MySQL, 3,775 in PHP, 3,693 in Apache, and 18,281 in Ubuntu, which is a popular Linux distribution. That's over 400 exploitable bugs in the application itself, but almost 30,000 more in the infrastructure that powers it. I pick on WordPress because I assume many of your professional sites are not taking advantage of the dynamic features its database offers, such as inventory management or searchable user pages, and instead have a page for your research you update maybe once a year, another for teaching that gets updated about the same, and maybe a blog you post to monthly. By folding a bunch of big, complex tools, namely here PHP and MySQL, into what is essentially static HTML files, the possibility of accidents is needlessly increased. The vast majority of academics don't need an industrial-strength database to power their professional websites. This is one of the reasons why Alex Heal, along with many people in and around DH, make so much noise about static site generators such as Jekyll. By compiling a site into HTML before the site is live, the number of moving parts exposed to the public are vastly reduced. While fighting over Jekyll versus WordPress might seem like a sideline to the issue of software accidents, this trend towards minimal application complexity in academic personal websites is part of a larger shift in software development, responding to the same concerns about accidents and complexity, of which I want to consider today the shift to functional programming in large-scale web applications as an example. The history of programming languages can be divided into a series of paradigms. Object-oriented programming is probably the most famous of these. However, the deepest and oldest fight over a paradigm, because of course you fight over a paradigm, why else do you have them, is the one between iterative and functional programming. Most of the languages you've likely used, BASIC, C, C++, Java, Python, Perl, Ruby, R, are all iterative languages. In iterative programming, the programmer issues a variety of commands to the system that mutates a global state, the collection of all data held in memory at a given moment. In contrast to iterative programming is functional programming, languages such as Lisp, Haskell, Erlang, Elm, Go, or ML. In functional programming, the programmer composes the solution to a particular problem by chaining together functions with no concern for global state. The logic of functional programming is that individual functions can be very small and well tested before being chained together, a process known as composition, in which the input to one function is generated from the output from a previous one, so they're all a chain of input-output processors. So in functional programming, while the program's overall behavior can be very complex, the individual pieces are simple and easily understood. Moreover, because the flow of data within the system is very heavily structured, where execution is happening and how data is being changed as the program executes is easily traced. Here's an example of calculating the Fibonacci numbers. Fibonacci numbers are the sequence of numbers starting 0, 1, 1, in which each number is the sum of the two previous. So 2, 3, 5, 8, 13, etc. In iterative programming on the left of the slide, and functional programming again on the right. The functional example, you'll note, does not define any state variables, nor does it change any variables in the process of execution. There are performance and readability payoffs for either approach, especially given the fact that the functional programming example uses a concept called recursion, where it defines itself in terms of itself, which looks like magic to a lot of people. However, the key difference is that the iterative program describes what the computer must do to get Fibonacci numbers, while the functional program describes how the problem is solved. Okay, for a variety of reasons that trace back to the work done in mathematical logic by Alonzo Church and Alan Turing in the 1930s, it is more possible to prove, in the logical sense, that a functional program is correct. For instance, in the functional example of Fibonacci here, I've added a layer of type checking using Facebook's flow system that guarantees that my function will only accept numbers and will also only return numbers. This contractual obligation, which prevents runtime errors due to unexpected input, is one reason why many big data companies are switching to functional programming. AucML is used by Bloomberg for derivative analysis, along with a lot of other financial companies in the United States. Walmart uses a language called Clojure for supply chain management. Twitter uses a language called Scala for a lot of disk-intensive work. Facebook uses a variety of functional programming languages for a variety of its projects, and they even fund the development of Clojure, which Walmart also uses. Thinking about software in terms of complexity, error, and accident, as I have been here, signals a broader shift in how we think critically about computation. To return to French theory, I'm sorry for that, Jean Baudrillard, who frequently cites Paul Virilio in his later work, sets the terms for a lot of humanistic thinking about computation. For the intro to theory of Baudrillard of simulacra and simulation, virtuality is a space of disembodiment, of immateriality, and a shimmering evanescence. He famously describes a desert of the real in which simulation has withered reality and left a dusty, desiccated heap. We might think about Facebook's famous motto, "Move fast and break things," as an example of this desertification. Get everyone online, damn the torpedoes. This is the logic of disruptive innovation. However, less widely known, in 2014, Facebook changed this original dictum to "move fast with stable infra," which I don't think looks good on a hat, but that's my opinion. But I think more importantly, this highlights why minimal complexity is such a potent site for studying security in the shadow of Virilio's great accident. Moreover, the infra, hopefully shortened from infrastructure, in the new Facebook motto underscores why I think infrastructure studies is so important to contemporary digital humanities. Paul N. Edwards has suggested that most of what should be studied as technology in public discourse, quote, resides in a naturalized background as ordinary and unremarkable to us as trees, daylight, and dirt, unquote. These background technologies, quote, are not salient for most people most of the time, unquote. However, these infrastructure systems, as Edward argues, are co-constitutive of modernity, that, quote, to be modern is to live within and by means of infrastructure, unquote. We could read Baudrillard as suggesting that simulation makes reality into a desert, but given the sheer amount of material stuff that proliferates out of sight to sustain a supposedly immaterial virtuality, is there a jungle growing where the desert should be? In conclusion, infrastructure studies provides a methodology for hacking our way through the tangle of competing material systems that sustain the disembodiment of code. By grasping the often dull materiality of virtual existence, by highlighting the jungle that sprouted where we were told a desert would be growing, infrastructure studies gives us the best means for understanding, articulating, and acting against the circulation of power in the present. By understanding how big data is now working to mitigate the accidents that proliferate as an unavoidable side effect of complexity, we can better see how the disruptive ethos of tech startups are mutating into something more careful, more considered, and probably more dangerous. If we hope to gain a better understanding of how anxiety and security are shaped and are shaping our lives, following the code seems like a good place to start. Thank you.